Okay, so everybody hopefully was able to see the video, and I'll take that comment under advisement. And again, there'll be another one on Friday. And I think I made it clear which revenue exam on Monday, right? And I sent out exactly which topics are going to be covered. Also, chapter 4, with the exception of one section over there. And again, don't memorize anything. Well, I should say don't memorize anything. You don't have to memorize that, crazy formula for reduction of order or undetermined coefficients. But there will be a problem involving those, and I will give you the formulas there. Okay, so just to let you know about that. And there are 4 problems, okay, because that method of undetermined coefficients tends to be long, okay? So I tried to choose a problem that wasn't very bad, but again, it takes time. So problem with, when you only have 4 problems is 25 points each. So you don't want to, that's the trade-off, I guess. I just sent out an email, you'll see, if you haven't seen it yet, the usual, story, right? Please come to class if you can 15 minutes earlier, although we will not start till 12:30, because I have to get all that administrative stuff out of the way. Collecting cell phones, checking IDs, etc. And the usual, right? No electronic devices, no calculators. Use the paper that I supply you, and whatever, just be honest, okay? Okay. And those people who are, taking the test at the alternative testing, you have to get on the ball and get a request for that, because I can't give them the test until they tell me that you've requested it. Okay, so today's topic is an interesting one, something new. Again, this will not be on this exam, okay? It's basically systems of differential equations. Okay, let me just give you an example of what I mean by that, and we'll contrast that to what we've done so far. This is just an example of the type of problems we want to look at today. So now, see, up to now, we've always had just one differential equation, one independent variable, of course, because it's an ODE, and there was only one dependent variable that we dealt with, okay? But now, I'm going to have a system of equations in the sense that x and y will be the dependent variables, and say t is the independent variable. So maybe, this is just an example, now x double dot minus x minus 2y is equal to t, okay? And another example would be this is really a system. Second y respect to time minus 2y plus 3x equals t. Okay. Now, based upon what we learned so far, we really can't handle that, right? If in the first equation we didn't have the 2y, oh yeah, that would be constant coefficients. The independent variable would be t, and the dependent variable would be x. Similarly, the second equation, if x wasn't present, you can do it. It would be y double dot minus 2y equals t. Again, constant coefficient, second order. Okay. But now we have this situation where we've got coupled equations. This happens all the time in applications. Okay, just think of Newton's law, right? Even if you have a particle in the xy plane, this is the acceleration along x, acceleration along y. It could be a function of its position in the xy plane, right? Similarly, there could be drag forces, a function of the speed, which would be what? The square root of x dot squared plus y dot squared, which is the speed, okay? So we have to know how to handle equations that is called a system of equations, okay? And now the ones that we're going to do, just because of algebra, there won't be more than 3 dependent variables. Most of them will have 2 dependent and 1 independent. And again, you have to be able to easily transition. It's always not y and x, right? Here, t is independent variable in both equations. The dependent variables are x and y, okay? And we want to know how to solve this type of equation. Okay? One of the things which the book doesn't mention, which is unfortunate, and something which you have to know, is how many constants are we going to get in the solution, okay? If this came from Newton's law, for example, and a particle is in the xy plane, we know that at t equal to 0, we have to know the position xy, and the velocity dx dt dy dt. So that would be 4 constants of integration. Okay? So here there'd be 4. And what happens in general, the number of constants can actually be determined a priori just by looking at the order. What you do is you look at each of the equations and you just note the highest order derivative in each equation for the dependent variables. This one is what? It has a second order in x and 0th order in y. There's no y derivative, right? This one no x derivative, but it has a y second derivative. So what you do is you look for, scan the equations, look for the highest order derivative in x and y, add those two numbers, that's the order. So this thing would be fourth order. And indeed, if you took this and you wanted to solve it by MATLAB, okay, given initial conditions, you'd have to write as a system of first order equations, and you'd actually get 4 first order equations, okay? So the fact that it's fourth order, that tells you, even before you start solving it, that in the general solution, there has to be 4 arbitrary constants, no less, no more, okay? And that's a very important fact to keep in mind, okay? Now, the equations we can do in this course are restricted to systems of differential equations, but with constant coefficients, okay? And let me tell you why why that restriction is in place, okay? It doesn't always happen, okay? There are plenty of applications where you have variable coefficients, okay? And as an example, the problem that we have with variable coefficients is that these operators do not commute, okay? If I had 2 differential operators, for example, suppose that L1 on x was 4x dot minus 6x plus 8y, and L2 on x was, 8 to be x double dot minus 6x dot plus 8y dot. I'm just making this up. Notice that basically that the differential operator hits the dependent variable, okay, and all the coefficients here are constant. It comes out, and I think we mentioned this maybe the first week, that if you have differential operators with constant coefficients, they commute. That is, you can easily convince yourself that L1, L2 on x is the same as L2, L1 on x. Let me give you an example, though, where that doesn't work, namely when you have variable coefficients. That's what I was scribbling up over here, okay? You can verify the algebra, but just let's concentrate on what's going on over here. So I have 2 differential operators. What does L1 do on a function x of t? It just does t squared dx dt plus 4x, okay? Notice the variable coefficient t squared. L2 operating on x is 3 dx dt. So you may say, oh, yes, that one is constant coefficients, but this one is not. And what we're going to do now is just do the 2 operations, L1, L2 on x, and then do the opposite order, and you'll see that they're not the same. Okay, so what's L1, L2 on x? You do L1 operating on, what's L2 on x? 3 dx dt. Okay? Now, when you do L1 on that, okay, remember it's just L1 on an object. You have to say it in words. What does L1 do to a function? L1 on a function takes the derivative of the function, multiplies by t squared plus 4n. It's 4 times the function. Okay? So, I'm going to do L1 not on x, but on 3 dx dt. So just go to here, every place you see x, replace it by 3 dx dt. So if I do L1, L2 on x, according to this thing, it's t squared d by dt of this guy, right, plus 4 times this guy, okay? If you expand it out, you get this. You get 3t squared, the second expected t, plus 12 dx dt. So that's the operation, doing L2 first, then doing L1. Let's do it the opposite way, okay? Let's do L2, L1 on x. This L2 operator is still there. What's L1 on x? T squared dx dt plus 4x, okay? And now we're going to do L2 on this mess. Well, L2 on anything is just 3 d by dt of that stuff. So I got 3 d by dt of that first line. When I expand that out and I compare it with the other one, you can see it's not the same. We do get 3t squared x double dot, but in this case, the only remaining term was 12 dx dt. Here we pick up a 6t dx dt and a 12 dx dt. So we've got another term over here that wasn't in the first one, okay? So that's why it's important, okay, the technique that I'm going to show you to solve systems of equations is restricted to systems of linear equations with constant coefficients, okay? And again, the best way to do this, we're going to talk just in abstract theory. Let's just do some problems because it's going to be very similar to what you've seen in your courses in systems of linear equations, okay? So the topic over here is systems of linear ordinary differential equations, ODEs, with constant coefficients. typical of that one. Let's start off with an easier one first, though. Now, before I do that, there's a notation that makes this very simple. And some of you may have seen this before. Again, it's just notation, okay? What we're going to do is the following. We're going to say, we make an operator big D on X. That just means dx dt, okay? It's just a definition, okay? So, this is called this, it's crazy, this denotation just makes it makes this procedure very mechanical and easy to do if you adopt this notation, okay? And what would d squared operating on x be? It just means take the second derivative of x with respect to t. It's just a notation, okay? So if you had a third derivative, d cubed x, okay? So it's a shorthand notation. Okay, let's look at our first example then, okay? And see how we would go about solving it. So the first differential equation is dx dt, right, plus dy dt plus 2y is equal to 0. 2, right? Dx dt plus dy dt plus 2y equals 0. Dx dt plus y dt plus 2y equals 0. And the next guy will be dx dt minus 3x minus 2y equals 0. Okay? So that's the system of equations. So x dot plus y dot plus 2y equals 0. X dot minus 3x minus 2y is equal to 0. Okay. The first thing we want to do is note what the order of the system is. Well, in the first equation, the highest derivative of x and y is 1, 1. Over here, it's still 1 on x. So the order of the system is 2. Okay, so you want to note, basically, the order is equal to 2. What does that mean? That means when we finally solve this system of equations, the general solution should involve 2 arbitrary constants, no more, no less. If you have more than that or less than that, you made an error someplace. Okay? Just have 2 arbitrary constants in the solution. Okay, now comes just the formality of just rewriting this. What you do, let's go to the first equation. Look at all the stuff with x in there. The only thing I see is a derivative on x, so I'll say dx for dx dt, right? Okay, now what happens with y? I have dy dt plus 2y. And the idea is to put all the stuff with y together. Write it as d plus 2 operating on y is equal to 0, right? Seems kind of silly, we're just rewriting it, but you'll see it makes it much easier to manipulate. So dx dt, and d plus 2 on y is just the derivative of y, that's the y dot plus 2y. Now we go to the second equation. Get all your x stuff in here. I see x dot minus 3x, so it'll be a d minus 3 operating on x, right? And then just looks like minus 2y, I guess, right? Is equal to 0. Okay? Okay, now what you do is basically just make it, you can basically operate with these d's almost like they were formal symbols. And what we're going to do is uncouple the system. That is, if I only had an equation in x or an equation just in y, I'd be okay. So here's what we're going to do. And again, which one you eliminate depends upon the complexity of the equations, okay? And I think the easiest thing to do, although you don't have to do it this way, is look at this equation over here. You have d plus 2 operating on y. Here you have a minus 2y. Suppose I hit this with the operator d plus 2, right? That'll give me minus 2, d plus 2 on y, right? And just multiply this guy by 2. You get 2 d2 on y, right? Okay? So now, what I've really done basically is, again, why did I choose 2 and d plus 2? Because I want to get rid of the y. Okay. What I'm doing the first time is just a way of saying, well, multiply the first equation through by 2. Okay? So that becomes 2 times the derivative of x with respect to t, plus, I guess I get 2d, I don't even have to factor it even, it's going to go out, 2d plus 2. Operating on y is equal to 0. Okay? Now remember, we're kind of just manipulating this D thing as though it was a symbol, but it actually is a differential operator, okay? And here's where it becomes very powerful. What we can do now is take this equation and hit it with the operator D plus 2. What does that really mean? Think about it. It means I'm going to take the derivative of each term and add twice each term to it. See? But just by hitting it with D plus 2, you're doing that, and it's a very complex way of doing it. So what happens here? See, now I got a problem. Do I do D minus 3 and hit with the D plus 2? Do I do D plus 2 first? Doesn't make a difference because the coefficient's a constant. Okay? So it doesn't, if you do D minus 3, D plus 2, it doesn't make a difference. Let's do D minus 3, D plus 2, operating on X, right? I'm hitting with the D plus 2 operator, minus 2, D plus 2 on Y is equal to 0, right? Hit with the D plus 2. Okay, remember, formally we're multiplying by D plus 2, but that's really not fair. What we're really doing is operating on it with D plus 2, which means every term is differentiated and added twice to it. But you can see how much, again, like I said before, it's very compact this way. D minus 3, D plus 2 on X, minus 2, D plus 2 on Y is equal to 0. Obviously, what you're going to do now, and this was done on purpose, add the two equations, right? All the stuff in Y